Thank you for the invitation to give this talk, and thank you all for attending. So I'm going to be talking about non-Gaussian orbit determination for near-Earth and cislunar space domain awareness. Before I get into that, I wanted to kind of first touch on just a little bit about Texas A&M for those of you who might not be aware. So A&M is one of the largest public universities in the US. It's also one of the few universities to have a triple designation as a land, sea, and space grant institution. Currently, we have a total enrollment of about 77,000 students on campus. In the College of Engineering, we have about 24,000, on our way to 25,000 engineering students. This is undergraduate through PhD. And in the Department of Aerospace Engineering, we are home to about 44 faculty members. Some of these have outside appointments in administration, but they basically serve as the core faculty for our department. Historically, we are continuously ranked in the top 10 amongst public universities for aerospace engineering. Currently, we're ranked 6th in our undergraduate program, 7th in our graduate program. And in the department, we have close to 1,000 students in undergrad and grad. About 70% of those are at the undergraduate level. The rest are at the graduate level, pretty evenly split between master's students and PhD students. Our department is organized into 7 strategic research areas. You can read them there. There are a few that are really interesting. We're a very large program in hypersonics. So we're currently building and about to field a several kilometer long ballistic aero-optic and materials test range that will look at high-speed reacting flows. We also are one of the only programs, and perhaps the only program in the US, that has a concentration area in space domain awareness. And since that's the topic of today's talk, I thought I would spend a little bit of time kind of highlighting that research area a bit. So we have 7 faculty members of those 44 who are affiliated in the space domain awareness area: Terry Alfrin, Rakdan Bhattacharya, Suman Chakravorty, myself, John Junkins, and Manaraj Amaji, and Raul Vidali. So these 7 of us basically form the cornerstone of that space domain awareness group. Between us, we have somewhere in the neighborhood of about 40 graduate students working in space domain awareness. So our mission in that area is basically everything that encapsulates space domain awareness. So here I just have a list of kind of all of the subtopics you can think of in space domain awareness. And so some subset of us work in one or more of these areas, and we're going to touch on several of these areas during today's presentation. But basically, we're interested in how do we enable perception, comprehension, and prediction of activities and phenomena in the near Earth, the cislunar, and the interplanetary domains. Fundamentally, we're basically trying to develop theoretical, computational, implementational solutions to solve those problems in order to ensure continued safe access to and safe operation in space. All right, so that's my little department spiel. So that's over, and we can start on the more interesting part. And so I just want to start with kind of a confluence of estimation problems. So I start with kind of my rough definition of what is estimation. So it's the process of determining the values of uncertain parameters. They can be constant or they can be dynamic, based on some sequence of limited, corrupted, and indirect measurements. So we have a bunch of data that tells us something, and we need to use that data to figure out things we actually care about, as opposed to just what the data tells us. In my group, I subdivide this into 2 pillars of research. The first one, the focus for today, is space domain awareness. Generally, here we're talking about multiple objects. This could be, one object we're focusing on. It could be a constellation of 5 objects. It could be the entire catalog of a few tens of thousands of objects. We typically think about doing computations on the ground, so we don't have necessarily a computational limitation in that sense. But with the emergence of space-based space surveillance, we might also think about doing computations on orbit in addition to on the ground. That complicates things, but nevertheless, at the end of the day, we can bring the data down to the ground and we can use as big of a computer as we want to. And we're trying to facilitate some level of comprehension, amongst other things. So the ... there is just basically any product you can think of based on what you do with estimating the state of a few tens of thousands of objects, that falls under the heading of space domain awareness. The second pillar is spacecraft navigation. So I broadly decompose my work and my research group's work into these two pillars. Spacecraft navigation, typically we're thinking about a single object or maybe, a couple of objects operating in conjunction with one another. We're typically doing computations on board those vehicles, so we are resource constrained in that sense. But at the end of the day, we still want some level of comprehension. We want to understand something about ourselves. We want to understand something about the environment in which we're operating. And we have follow-on products that we do from there. So we would use a navigation solution to formulate a guidance solution, formulate control actions, and form a real-time recursion. These two problems are very different, but they're also very similar. And so it kind of leads me to a set of three research themes. The first of these is tractable Bayesian and or non-Bayesian inference that's applicable for both single target and multi-target tracking. It's a problem that has some posed solutions theoretically, but it's still something that's very ripe for research to this day. The second one is state and parameter estimation of highly uncertain dynamic systems. This could be systems where we know very little about the models. Maybe it's a maneuvering system. Maybe it's a system operating in an unknown drag environment. Maybe it's something where we just don't know much going into it and we have to do a lot of learning. And then the third one here is effective sensor resource utilization and sensor data exploitation. And it's kind of this last one that is something that we're interested in here, specifically the data exploitation side of things. What happens in both of these problems is that you have data, and that data is very precious. And so you need to make sure that you're making the most use of it as you can without leaving things behind. So a little bit of motivation for the problems in space domain awareness. We have kind of two emerging problem areas in SSA. One is proliferation of objects in the environment. So this is a graphic from OneWeb from several years ago that nicely illustrates kind of their plans to develop a low Earth orbit constellation of vehicles that will provide coverage basically for space-based communications. They're not the only company doing this, right? You have SpaceX doing it with Starlink. You have Amazon doing it as well. But this is one of those constellations. When you start to think about these objects being added onto what already exists in space, you come into a couple of different challenges. One is that you have a wide range of object motion. So these are objects that are going to be placed in low Earth orbit. That's going to become a very populated orbital regime in the next 5 to 10 years. But you also have several objects operating in like the regime of GPS satellites. And then you have a lot of objects operating out at geosynchronous orbits. And so you have to deal with this wide range of motions where things are moving fast, medium, slow relative to the ground. Objects in any of those domains may be maneuvering. You may know about the maneuvers. You may not know about the maneuvers. The maneuvers may be logical. They may not be logical, at least in accordance to what you think logic would be. You have to deal with closely spaced objects, things that look similar to one another from your sensor's perspective, things that are passing in front of or behind one another, things that may come into contact with one another in space. And of course, we've seen the consequences of those closely spaced interactions recently. And then ultimately you have limited sensor resources. So you have a handful of ground-based sensors, you have even fewer space-based sensors. And so you need to basically have an awareness of everything going on in space using just a limited amount of information. The other emerging problem area is that of an evolving environment in which we do space traffic management. So for the first 70 or so years of human activities in space, we have mainly stayed in the near Earth regime, so low Earth orbits out to geo orbits, with only a handful of excursions beyond that. Nowadays, we're seeing a surge in activities going out to the moon, a lot of private companies trying to land vehicles on the moon. Therefore, they have to pass from the Earth to the moon. They pass through a fairly narrow corridor, and they have to play well with one another. Otherwise, things are going to get very bad in the Earth-Moon system. And we also see that people are planning to use these cislunar regimes to form launching platforms for moving on towards Mars. And so we're confronted with, we need to go from doing space traffic management down here to doing space traffic management in this area to doing space traffic management all the way out to Mars. And when we think about this, there's a few other challenges that kind of start to pop up. We had a variety of object to observer motions in the near Earth domain. Whenever we go out to cislunar distances or we go out to Martian distances, we have even more variety. So we have a very slow observer to object geometry. Things don't change a lot as we look at them from the ground. This means that there are going to be longer times between revisits. So whenever we go and we look at something near the moon, because it's not moving very fast relative to us, we might not look at it again for a while, right? And so because of that, we need to basically deal with these time gaps that exist. The needs, if you kind of stack all these challenges up, are that we need to be able to process data more completely. So when we take data, it is precious to us. We need to use it to the best that we can. And I would argue that we're not currently doing that. And we need to be able to predict where things are going to go between these measurements, especially when we're talking about measurements that might be spaced by 2 weeks or something. We need to know not only where is the object, but where might it be in the process. And so this is basically our uncertainty propagation and our data processing step. And so those are two of the main topics that we're going to talk about today. So as an outline for today's talk, I'm going to start by talking about uncertainty modeling and look at some options for what I would call non-restrictive uncertainty representations. We're going to talk a little bit about uncertainty propagation. How do we predict where an object is going to go with its uncertainty while using those non-restrictive representations? When we get data, how do we process that? And how do we do it in a way that we can say we are exploiting the data to the best of our ability? And then 2 applications, time permitting, one for cislunar orbit determination, and one that's a little bit more of a real world application for near Earth space domain awareness. So let's start with the uncertainty modeling. It's very common in SSA or SDA, depending on if you're using the old acronym or the new acronym, to make a restrictive assumption about uncertainty. And so this graphic here is just a screenshot from STK, and you see all these green blobs in the background. These green blobs are objects in the background that basically are being modeled as having an uncertainty that is Gaussian, right? There's ellipsoidal representation of uncertainty. So the implication is that the uncertainty is Gaussian. This, I would argue, is overly restrictive. We make this assumption for a couple of reasons. It makes the problem easier. We know very well how to work with Gaussians. We have a lot of very powerful tools for how do we manipulate Gaussians, how do we transform Gaussians. And so having a Gaussian PDF lets us do a lot of stuff very easily. It possibly leads to, and probably leads to, a loss of realism. And so this little graphic in the middle is basically showing if I took a set of realizations of the position and velocity of a space object and I propagated them for a period of time, what happens? The reality is that they spread out along the orbit. They do this so-called bananification. They form kind of a banana shape or maybe a boomerang shape where they curve along the orbit path, right? They don't exactly go just to the same orbit, but they kind of have some spread about that and some spread along it. If you make a Gaussian assumption, you get something that looks like these uncertainty contours. And that quite clearly is not representing this curved non-Gaussian distribution. So that's where you lose realism. If you use this solution and you try to go look for this object, as long as it's in this neighborhood, you're going to find it. If the object is out here, you're probably not going to find it. And this only gets worse with the longer the time is that you propagate over. So what we argue is that we need something where we can get these nice curved distributions, right? We want something that basically allows us the flexibility when a distribution is non-Gaussian to model it as being non-Gaussian. And so the things that you naturally think of are taking something like a particle-based representation. As long as I can sample from a distribution, then I can generate samples and I could use those. Or maybe taking some sort of a mixture-based method, and we'll look at those here in a second. The fundamental idea is that You want something that gives you that ability to make the curved distribution, but you really need your solutions to stay tractable. You still need to be able to solve things in a reasonable amount of time. And the idea, the hope is that you gain more realistic analyses. So now if I use these uncertainty contours to go look for the object, if it's out here, I stand a good chance of figuring out that it is out there. So what are some options? Let's say we have this very simple univariate case where we have a distribution that's clearly not Gaussian. So we're just trying to say we've got some PDF, P of x, in the variable x, and we want to think about ways in which we can represent that. The first one, the one we said is not good, would be to make an assumed density representation. So if I compute the overall mean and variance of this guy and I get a Gaussian representation, that's what I have. It's clearly not a good representation of the blue PDF, right? It misses in multiple areas. It doesn't predict the mode, doesn't predict the shape, all sorts of things. And this is just one point in time. So that's not going to work. We said there are basically two options that we could use. One is a particle representation. So as long as this distribution is something from which I can sample, then I can generate samples and I can basically populate my space with as many samples as basically I can tolerate. This is great, right? As long as I can generate samples and I can have 1,000, 10,000, a million samples that represent where my object might be. And the collection of them, the density of that collection, is what basically guides me to understand pockets of more or less probable areas. The problem is that you get these gaps. And unless you're very careful with your sampling, you're always going to have some gaps. You're going to get very poor tail behaviors because they're basically rare events. And so if you're trying to capture what's going on down in this region, you're not going to do a very good job. So it's a great option. It works very well with black box systems, but it's not the option that we're going to pursue. The option we're going to pursue is to use a finite mixture. So a finite mixture fundamentally is any set of parameterizable PDFs that you basically mix together with a set of weights to form an overall distribution. So in this case, we have just a set of 4 Gaussians. They each have a mean, they each have a variance, and they each have a weight. And when we weight them and add them up, we get a nice model for the blue distribution. In fact, it's a perfect one because I made this problem up. So, in that case, we have a nice representation, right? And so that's what we want to use because we can do nice tail behavior kind of analysis. We don't have any gaps in our knowledge anywhere. And so it makes for a very nice, flexible architecture for doing inference. So let's take a look at just an illustration of how you might use this in an astrodynamics context. The simulation that we consider here is basically angles-only tracking. So we have right ascension and declination measurements of an object that's in a near circular orbit. It's got these orbital parameters and some others. The observer is located in New Mexico. And we're taking measurements at once every 10 seconds. The measurements have zero mean additive white Gaussian noise with a standard deviation of 1 arcsecond added to them. So it's a pretty precise measurement, but we want to use this angles-only information to formulate some sort of an initial orbit determination solution on this object. The solution that we're going to use, the method we're going to use, is based on the admissible region. So in this context, we want to add constraints because the admissible region basically tells us every set of range and range rate coordinates that agree with the angles data. We don't want to search that entire space, so we add some constraints. We know that this thing's in near circular orbit. So we add a constraint that's just above geo for the semi-major axis. We add a constraint that the object is mostly going to be in a circular orbit. The admissible region works off of an attributable, and for that we need to take angles-only data and we need to produce angle rates. So we take the sequence of angles-only data and we do a linear least squares curve fit to that data in order to get an equivalent angle and angle rate out of it. The data is weighted in this least squares process by the inverse of the covariance matrix. Since it's a white noise sequence, that actually doesn't have any bearing on the problem. You'll get the same solution with regular old least squares. And then we're going to basically try to fit a Gaussian mixture to that constrained admissible region. And in doing that, we have to select sizes of the Gaussian components that get stacked together to make that approximation. And so we put some bounds on how big those can be. The smaller, the better. The smaller, the more number of components we're going to have. So there's a balance between your approximation accuracy and your computational burden. Oh, and then finally, to see kind of the power of this method, we're going to transform the initial orbit determination solution into a couple different coordinate systems just to look at how uncertainties change between different coordinates. So this is our admissible region. So it's in range in Earth radii and in range rate in kilometers per second. The black dotted line is the zero energy curve. So all of the bounded orbits, the Earth bounded orbits live inside of there. That goes out to something like 7 Earth radii, which is massive. We don't want to search all that space. That's why we add constraints. The blue constraint here is maximum semi-major axis. The orange constraint is maximum eccentricity. And so everything that's in that intersection, that's our constrained admissible region. So this is still about 3/10 of an Earth radii, which is still a huge volume of space. And it's still going kind of about 6/10 of a kilometer per second between max and min there. This is the space that we want to basically fill in with a bunch of Gaussian components in order to make kind of a flat surface, okay? We basically say that given the angles data and no other information, we can't say one of these points is more preferable than another one, so we assume that there's a uniform distribution. So we model this as a uniform distribution using a bunch of Gaussians. We pair that up with the data that we have from our angles and our angle rate. And we have a full 6th solution in range, right ascension, declination, and their rates. We take that GM and we project it into Cartesian coordinates. And this is a pairs plot of that, or a corner plot. So these are just the univariate marginal distributions down the diagonal. And then every off-diagonal one is just a bivariate marginal distribution. So here you would have the marginal distribution of the x position and the z velocity, for instance. These three are the velocity, or this bottom corner is the velocity components. Everything looks pretty nice there. You have kind of a flat center of this PDF, and then it falls off, and that's basically the angular and angular rate uncertainty. The true state is marked in an X here. If you look at the correlations between position and velocity, it also looks really good. If you look at position itself, the marginals look good. The univariate marginals look good. The bivariate ones don't look very good. The problem here is that, and there are no units on these plots just to keep things from being too crowded. The problem is that you've basically taken a very precise line of sight measurement. And so all of your uncertainty is in how far away is the object. So the distribution here is basically a very long, thin line that's very hard to model in Cartesian coordinates. Okay, so it's there, but it's very susceptible to basically errors. And so this would not be a great selection for representing the uncertainty in your state. If you transform it over into alternate equinoctial orbital elements, on the other hand, you get bivariate conditional PDFs or marginal PDFs that look pretty good. So here you have kind of your mean motion, you have components of the eccentricity vector, so on and so forth, mean longitude down here. Every one of these looks very well behaved. It has kind of that flat center, it tails off. It looks like something that is much more manageable to approximate. So the point here is just that with GMs, we can successfully approximate this distribution in range and angle space. We can do it in Cartesian coordinates. We can do it in an element space, and we can transform to any other coordinate system that we like. For this illustration, it just gives us an initial understanding or initial kind of representation of where the object might be. And then from that point, we need to propagate the uncertainty. So we have effectively this initial distribution at time 0, and we want to move it through time, right? If we have discrete or discretized dynamical systems, then this means that we need to solve the Chapman-Kolmogorov equation. If we have continuous time systems, we need to solve the Fokker-Planck equation. We're going to work in discrete time systems because that's complicated enough. If our PDF at some time is a Gaussian mixture, and if our transition density, which is our probabilistic model of the dynamics, is Gaussian, then the solution is component-wise propagation. That is to say, if I've got this PDF at some time, and it's a GM, I want to know PDF forward in time. I just need to take every component. I need to propagate each one of them. This gives rise to a variety of flavors of propagation equations. If you use linearization, it's an extended Gaussian mixture. If you use the unscented transform, it's an unscented Gaussian mixture, so on and so forth. The end result is that you get kind of a time sequence of distributions, all right? This thing looked fairly Gaussian here at the beginning. It actually wasn't. There's actually 3 components inside of there. And so over time, you see that this becomes non-Gaussian just because of the dynamics of the problem. Underneath this, there are components, right? So these are hard to see if we peel away the overall PDFs. This is just one component being propagated through time. So it is Gaussian. It stays Gaussian the whole time. But if this is a nonlinear dynamical system, it only stays so approximately. And so we need a way to basically know when is a Gaussian good enough and when is a Gaussian insufficient to solve the problem. That brings us to adaptive Gaussian mixture propagation methods. These are methods that adjust the number of components, the weights of the components, and or the parameters of the components in time in order to adapt to nonlinearities, non-Gaussianities that emerge. It will tend to increase computational complexity, but it will improve your component-wise and overall accuracy. The adaptation occurs whenever you detect some departure from what you might consider to be ideal behavior or acceptable behavior. And so basically what happens is you detect something is kind of amiss. You have this overall Gaussian and you replace it with smaller Gaussians. You want to stay inside of that Gaussian mixture. So you take one Gaussian, you break it down into smaller Gaussians. And by breaking it down into smaller Gaussians, you assume that you basically, you don't necessarily assume, but you get the property that any operation you do on that smaller Gaussian will be more precise than on the larger one. You can break it into 3, you can break it into 5, you can break it into 97. You can break it into whatever number you want to, but the idea is that you basically do this through time. So if we go back to this problem here, let's say for this component we're propagating along, and then here at time step 5 we say that Gaussian is too big. I no longer believe its solution. I take that thing and I break it down into 3 or 5 or 7 or something like that. And now I have smaller ones and they replace the 1 and we keep going. And we keep monitoring the agreement through time. Okay, so an illustration here, use a surrogate model for uncertainty, for orbit uncertainty propagation. So we're going to propagate uncertainty for semi-major axis and for the mean longitude. This is a nice bivariate problem that has a lot of the characteristics of a full 6-DOF, well 3-DOF. Orbit propagation problem. The semi-major axis is constant, but the mean longitude dynamics are nonlinearly related to the semi-major axis, and so that's going to lead to non-Gaussian behavior. We're going to apply a couple different methods here. One is the adaptive Gaussian sum filter. This is basically an approach that takes a fixed number of Gaussian components, and it seeks to find a set of optimal weights that are solved via a quadratic programming problem. The second one is what I'm going to call the original version of AGIS, which is now about 15 years old, where adaptation is triggered via disagreement between a linearized and a higher order propagation of uncertainty. And then the splitting library, which is what you saw on the previous slide, is based on L2 minimization, basically finding the optimal set of components of a GM that match a Gaussian by minimizing the L2 norm. And then I'm going to look at an updated version of AGIS where we use an information theoretic method to detect nonlinearity effects, and we're going to use a self-consistent information theoretic splitting algorithm. It's very similar to this one, just a different cost function that we are minimizing. So this is the result here. This is the result in eigenspace. So we've basically transformed the Monte Carlo samples into an eigenvalue decomposition based on the overall mean of the Monte Carlo population and the square root factor of the covariance matrix for that population. And we do the same transformation to the contours of all of the uncertainty propagation methods. We do this just to bring out some of the curvature. This looks like a bit of a mess here, so just a little bit of interpretation. Out here in purple, you have the adaptive Gaussian sum filter. Here in yellow, you have the original AGIS, and here in green, you have the new AGIS, AGIS Plus. And they're all fairly similar. They're getting kind of that curved shape. The adaptive Gaussian sum filter is kind of going after tails a little bit more than the others. The new AGIS has a different mode than the others do. Those are kind of the key characteristics. So overall, Aegis and the adaptive Gaussian sum filter, they perform fairly similarly. New Aegis produces a different mode. The thing that is not here is that if you look at the moments, the means and the variances that you get out of this, the adaptive Gaussian sum filter is not moment preserving. And so its mean computation and its variance computation actually are pretty poor in performance compared to the two Aegis versions. So I had to rank order them. Aegis Plus is kind of performing the best. Aegis is performing a bit worse, and then the adaptive Gaussian sum filter is performing a little bit worse. So that's basically, if I have initial distribution, now I can propagate it. And finally, I want to figure out how do I take data and process that data. So we start here with Bayes' rule. So I have some prior understanding of where the object is. I have some likelihood function, which is my probabilistic model of the nonlinear measurements that I get. And if I do the product of those, that's proportional to the posterior PDF. So it says Bayes. Recently, there's been some popularity in homotopic methods. So you can basically take the logarithm of the non-normalized Bayes rule, and you can introduce this parameter S, which we call pseudo-time. So it acts like time, but it's not physical time. And that controls the flow of information into the posterior. So you get this homotopic posterior that starts when S is 0 at the prior. And as you fold in information by flowing S from 0 to 1, the homotopic posterior becomes the Bayesian posterior. You can think about this in terms of a collection of particles. So you start with particles that are fairly spread out at S equals 0. At some intermediate value of S, let's say S equals 0.5, those particles have started to move. They've started to recenter themselves, and they've started to kind of collapse down. That's the incorporation of the new information. And then as S goes to 1, they basically finish their concentration, their collapse, and their mean shifting at the same time. You can also view this from an information theoretic perspective, as Bayes' rule is basically the simultaneous minimization of the KL divergence between the prior and your posterior, and the maximization of the expected log likelihood. And you can fold in that pseudo-time and basically have this homotopy parameter that when S is 0, you just get back the prior, and as S goes to 1, you get back Bayes' rule. So these are kind of all the rage right now in a lot of particle filtering, particle flow applications. We're going to look at an alternative viewpoint, which is to partition the likelihood and form a recursion of partial updates. And what we're going to get is a version of particle flow that we're going to call parameter flow, because it's going to give us a set of equations that tell us how parameters of a PDF move. So we're going to work on a Gaussian likelihood. So this is just shorthand notation for a measurement Z that's a nonlinear function of the state with some measurement noise covariance. This is just writing it out in terms of a Gaussian function. And we're going to make a very clever substitution of a value of 1 in here. This was introduced last year by Michelson, Popov, and Zanetti. They just take this sum from k equals 1 to n of 1 over n. This is just the number 1 at the end of the day. So they've done nothing to change the likelihood function. The clever thing is that you have the exponential of a sum, which is going to turn into the product of exponentials at the end of the day. We basically took this and we said there's no reason these have to be just 1 over n. I can replace them with these SKs, so long as the SKs are positive and sum to 1. And I can basically make whatever number of steps I want to make. So I can make 2 steps in there. I can choose S1 to be 0.1 and S2 to be 0.9. I can make 10 steps. I can make them all equal distance. Whatever I want to do, I can do it. You then rewrite that exponential of the sum as a product of exponentials, and then this is basically just a product of Gaussians that has some scaling terms involved. So the really clever thing is that you've gone from a Gaussian likelihood to a product of Gaussians as your likelihood. And if you think about Bayes' rule, which is the product of the prior with the likelihood, you have products, right? So if my prior is Gaussian, then I have a Gaussian that multiplies all of this, and I just have n products of Gaussians. And one of the great things about working with Gaussians is we have all of that knowledge of how to manipulate Gaussians. And so this just gives us a sequence of recursions. You apply standard results for the product of Gaussians n times, and if your prior is Gaussian and measurements are nonlinear, then Bayes' rule is basically going to approximately close. So what it turns out as is a set of recursive equations for the mean, and in this case, I'm writing this in terms of an information matrix or a precision matrix, where you start with some initial mean and you add on a bit of information. And then you relinearize the nonlinear measurement function and you add on a little bit more information. You add on a little bit more information. You do that n times and you get to a new posterior mean and covariance, effectively. This lets you discretely relinearize the measurement function. So you have nonlinear measurements. The conventional way is you linearize that once. You get the extended common filter when you do that. Here you can relinearize as many times as you want to. The really great thing is that there's no reason that I have to stick to this discrete relinearization. I can consider what happens in the limit as those partitions go to 0. And what I get is a set of differential equations that allow me to continuously linearize my nonlinear measurements through the update, okay? So if you think about covariance propagation, you continuously linearize the dynamics and you get a dynamics Jacobian that evolves in time in order to propagate covariance. This is basically linearizing the nonlinear measurement function through time and allowing me to numerically integrate my update. That's really cool. If all of this is constant, then basically you just get the information form of the Kalman filter, is what happens, okay? So graphically what's happening is if you have 3 times tk minus 1, tk, and tk plus 1, error grows, you do an update, error grows, you do an update, error grows. And that's kind of the classical thing that we're used to seeing. This is that single step update where we go from prior to posterior. This is what we do currently. I'm going to break this and I'm going to say that this time and this time there's actually a tk minus and a tk plus. That's pseudo time equals 0, pseudo time equals 1, basically before the update starts and after the update finishes. So I've not changed anything other than this single update now is just slanted because it's going from prior time to posterior time, same physical time, just different pseudo time. This is still the conventional method, a single step update. So all of this update happens at once. In this new parameter flow method, we have a continuous update. So we numerically integrate from the prior to the posterior, okay? And it lets us continuously linearize. We do see this trend where basically we do a lot of processing early on and then we kind of plateau towards the end. We've been talking about Gaussian mixtures. So the question is, what happens if you have a Gaussian mixture? The same thing, okay? Basically, the means and the covariances or your information matrices or your precision matrices, they have the same form, just on a component-wise basis. The difference is you get a recursive update for the weights of the Gaussian mixture. So you have to update them recursively as well. Or you can also do that limiting process and you can get a differential equation for the weights and you can numerically integrate weights, means, and covariances through an update. So let's put this together in a bit of an illustration just to kind of make it make sense. We have a set of prior information that's characterized by a 3-component bimodal Gaussian mixture. So this is our prior. We take a nonlinear measurement of range that has additive Gaussian noise. So this is our range measurement and the uncertainty contours for it. And then Bayes' rule says this would be the posterior, this little curved guy. We want to produce a good approximation of that Bayesian update. And so we're going to look at kind of a little bit of a combination of discrete parameter flow and continuous parameter flow. So we start with that as our prior. It's actually 3 Gaussians underneath. And so those are the 3 Gaussians. And we're going to do a discrete update just because it's a little bit easier to look at. So we do part of the update. Those 3 Gaussians become these 3 Gaussians. We do another part of the update and another part and then our final part. So we split this into 4 update steps to go from prior to posterior. All the while it's 3 components, and all the while we're basically relinearizing that nonlinear range measurement. We can take these 3 components and put them back together, and that's our final GM posterior. And compared to the Bayesian posterior, it's a pretty good match. It's not a perfect match because nobody said that 3 components was sufficient to represent that distribution, but it's a pretty good match for what we've done. That's the discrete version, right? Most of the update happens right there, and then you see that from that point on, it's kind of just reinforcing the information that you've gained. We can also look at the weights, and here we'll look at discrete weight updates and then what happens in the limit for continuous weight updates. So if you do a traditional update, you go from prior weights to posterior weights in 1 step. If you break this into something like a sequence of 4 updates, You do a lot of update, and then you do progressively little less update. These don't end up in the exact same place. They're close, but not exactly the same as what you would get in the conventional update. If you do more discrete updates, you see that that information gain in the beginning is much higher than the rest. And if you pass this into the continuous update, that's what happens for numerically integrating the weight update. So you get this very nice continuous flow, smooth flow of information from the measurement into the posterior distribution. Okay. Those are all kind of toy problems, so let's look at an application for cislunar orbit determination. I'm going to look at distant retrograde orbits here. This is a family of them, so this is the Earth, this is the Moon. You have L1, L2, L3, L4, and L5, so the Lagrange points. The bolded black trajectory there is the one that we're going to study, and just as a source, I've taken this family from Emily Zimmerman's PhD thesis. We're going to basically propagate uncertainty for this guy, and then we're going to look at measurement processing. So we start with an initial uncertainty of 10 kilometers in position, 1 meter per second in velocity. If you draw a few hundred samples and plot the trajectories, you kind of get this fattening out, right? So basically, that's our nominal trajectory. That's what happens when we have uncertainties in it. Like in near Earth space, you get kind of these pinch points where things come together, and you get points where things kind of, diverge from one another. We're just going to focus on a few points in time. So this blue condition is about 29% through the propagation. I'm going to call it the near Earth or the towards Earth condition. This purple one's halfway through. I'm going to call it the away from Earth condition. Going to get an L5 close approach, and then what I call the south face, because this kind of looks like a smiley face. The south face condition down here about 88% of the way through. You can tell that's got some nice curvature going on. So that's where we want to see these Gaussian mixture methods work. We're going to use the EKF, and we're going to use the original version of Aegis, just adapted for the circular restricted three-body problem. And we're going to compare the two against samples. So this is our little map of the conditions we're looking at. We start off with that towards Earth condition. In black, you have the uncertainty contours from the EKF. In blue, from Aegis, from the GM method. They're basically on top of each other, right? There's not a lot of difference here. You can see a little bit of difference, but not too much. If we go to the away from Earth out here condition, now you see that the GM version is kind of bowing away from the linearized version. If we go to the near L5 case, it's kind of collapsed back. And so this is, again, a traditional characteristic where things start pretty close in agreement. They kind of diverge. They kind of oscillate back and forth between agreeing and not agreeing. And then finally, if we get to that south face condition, you see nice curvature from the Aegis method here, and you see this tangent plane approximation from the EKF method. And so that clearly is not representing this curved PDF. But we got this by modifying an existing method. Not a lot of work, actually, to modify that method, and it does produce a very nice representation of the uncertainty. So let's look at what happens when we process data. This is a very made-up problem, okay? So we're going to take a range measurement from the center of the moon. Not possible, but just for illustration, all right? That range measurement has additive noise that has a standard deviation of 25 kilometers. Again, not a real problem. We're going to do Monte Carlo analysis, and basically, just for the sake of time, here's the results. So here you have the EKF. You have a particle flow version of the EKF, so basically doing that mean and covariance propagation through the update. You have an extended Gaussian mixture filter, and then a parameter flow version. The short story is the GM versions do better than the non-GM versions, and the parameter flow versions do better than the non-parameter flow versions. So shockingly enough, if you give the filter all the bells and whistles, you give it the Gaussian mixture, and you give it the parameter flow, it does the best. It has the best outlier performance, basically. That was a good result, but it's not that like shock and awe thing that we want. So let's take a look at an edge case and look at uncertainty contours. So this is our distribution. We're going to take a sample that's way out here on the low probability tail, and we're going to look at what is the posterior uncertainty contour look like for those four filters. And this is what you get. The red star is the truth. This is the posterior uncertainty contour for the EKF, for the parameter flow EKF, for the extended Gaussian mixture, and for the parameter flow extended Gaussian mixture. This is a really hard problem. These three don't represent the truth very well. This one, the truth is right on top of the uncertainty contours, okay? These are all in different scale. And so what we're going to do is in this next transition, which if you're going to pay attention to anything, this is the transition to pay attention to. We're going to scale everything to this scale here. So everything's going to be comparable in a size matter. And so that is now the same scale and the uncertainty contours from this parameter flow method, all right? So not only is it the only one that's centered on the actual true state of the object, it's also a much tighter uncertainty than the others. And so that really gives us credibility into this method. I think we're running a little short on time, so I'll go through this problem very quickly. Basically, I wanted to do something that was pseudo-realistic, right? Everything we've done is kind of a toy problem, and I wanted to put the method into something relatively reasonably representative of real life. And so I did a near-Earth space object tracking problem where we take angles-only data from the observatory located at Haleakala. And basically we take data for 14 nights between the hours of 10 p.m. and 4 a.m. Tracklets of this data are capped at 6 minutes plus or minus 1 minute. Data every 20 seconds, zero mean, additive white Gaussian noise, 1 arc second, 1 sigma, okay? So fairly standard angles-only tracking problem. The object is a GPS orbit. This is our observer here. And so that's the guy that we're trying to track. This is the data that we have. So right ascension, declination, there's a gap here. So for 3 nights, I basically excluded observations, kind of a real world situation where you don't see the object for a few nights. It's hard to see kind of what's going on with the measurements when you plot it against time. And so we plot against measurement index just to show kind of each of the little tracklets. So there's a total of 183 measurements over the span of 14 days that we have to work with. These are the position estimation error results for the parameter flow extended Kalman filter. So we're just taking an EKF and we're giving it that continuous numerical integration update, plotted against measurement index. So this is your first night of data. This is your second night of data that comes in here, your third night. Somewhere in here is that 3-day gap, and then you resume, and so on and so forth. So these orange curves are the plus minus 3 sigma intervals, and the blue curves are the actual estimation error. I'm just showing one trial here. You can Monte Carlo this and it'll hold together, but this is using that parameter flow method on top of an extended Kalman filter. And so you can break this just like you can break an EKF on this problem. And what that indicates is you've got those non-Gaussianities entering into the problem. All right, so a few conclusions here. What we've talked about today, models for non-restrictive uncertainty representations, getting into uncertainty propagation for long-term propagation, and then doing complete information extraction and data exploitation. What we didn't talk about, which is also interesting, is effective sensor resource management. So if you've got these better representations, how do you use those to task your sensors to go get very informative data? From the uncertainty modeling perspective, it's possible to use existing frameworks, but where the state-of-the-art is lacking right now is in analysis tools. So basically, we have methods, but when you get into non-Gaussian uncertainties, analyzing them in a good, consistent way is a little bit harder to do than when you have Gaussian uncertainties. For uncertainty propagation, we've shown it's possible to adapt existing tools to emerging domains, but we've only looked at this in terms of Cartesian coordinates for the restricted three-body problem. And so one area of investigation is what happens when you use different coordinate systems to represent the state of your object. And then finally, we have shown that these parameter flow methods have incredible promise. And they basically give us this ability to kind of do more with less, right? I'm extracting more information out of a single measurement using this method, but it's still very early in its development cycle. So we still need to develop robust and potentially non-Bayesian data processing mechanisms using this kind of philosophy. And with that, I would like to thank you for your attention. And if we have time, I'll take any questions.